All right, welcome back. We're going to do our last integrated rate law case for a second order rate law where the exponent in this equation shown here on the right hand side is 2. Second order integrated rate laws are solved like this. We take the negative change in concentration of A with respect to time as equal to the concentration of A raised to the second power and multiplied by our rate constant K. Again, to solve this equation, we'll need to group like terms on the same sides of our equation. I'll accomplish that by bringing the term A squared over to the left-hand side, dividing it through, the negative sign and the term dt over to the right-hand side. Once more, we'll integrate over the bounds from 0 to t on the right-hand side, and from initial concentration of A at time 0 to concentration of A at time t on the left-hand side. This time, to integrate the left-hand side, we'll raise the power of A by 1 and divide by that new power. We end up with, on the left-hand side, negative 1 over the concentration of A, integrated over the bounds from A at time 0 to A at time t, equal to negative K times t, integrated over the bounds from 0 to t. Simplifying this a bit further, we get a negative sign out in front of 1 over A at time t minus a negative sign out in front of 1 over A at time 0 is equal to negative K times t. I'm going to multiply everything through by negative 1 to get rid of those pesky negative signs, and I'll end up with 1 over A at time t minus 1 over A at time 0 is equal to positive kt. Once more, I'll rearrange it so that I have something that looks like a linear equation. I'll add the term 1 over A at time 0 to both sides. This is the integrated rate law for a second order reaction. Again, we can approximate it as a straight line relationship if we consider this whole term, 1 over A at time t, as our vertical axis. This term, just our rate constant K as our slope, time as our x variable, and the entire term 1 over A at time 0 as our intercept b. If we sketch a plot for what this relationship might look like, we'll now put on our vertical axis 1 over A as a function of time. On our x-axis, again, we'll place time. In this event, 1 over A at time 0 is still greater than 0. Perhaps it's somewhere here along our vertical axis. In this relationship, our slope is positive. There's no negative sign out in front, meaning that this relationship is going to trend upward as a straight line. This straight line has a slope equal to positive k, our rate constant, for a second order relationship. Every second order reaction will have a relationship between 1 over the concentration of A as a function of time that looks like a straight line with a slope that's equal to positive k.